Deep Learning for Computer Vision. In this section, we are going to look at computer vision problems that we can solve with deep learning, specifically using the supervised learning approach. In this section, we are going to take a look at solving computer vision problems using deep learning, more specifically the supervised learning approaches for image classification and object detection. We are also going to take a look at transfer learning for quickly training your deep learning models. Deep learning in fashion. In this video, we're going to build an image classifier to recognize fashion items. The aim for this video is to build an image classifier using convolutional neural nets. We're going to use TensorFlow to analyze the performance of our model. We're also going to propose plausible ways to further improve our model. So let us first discuss the motivation behind image classification. Image classification is, simply put, the problem of assigning a label to an input image. So given an image, our model needs to predict whether there is a cat or an airplane in the image. This is also one of the core problems in computer vision, which has tons of practical applications. So these are the 4 steps that we need to follow in order to build our image classifier. First of all, we need to prepare our dataset of images. Then we can build, train, and evaluate our model. In the next few minutes, we're going to see a hands-on demonstration of each of these 4 steps. So let's begin. For this demo, we're using the Fashion MNIST dataset. It consists of 60,000 images for training and an additional 10,000 images for testing our model. These are 28 by 28 grayscale images and there are 10 different classes. Now, you may have also heard of the MNIST dataset that most AI researchers till date use to train and evaluate their models. So the question is justified, why Fashion MNIST? So we have been using MNIST to train and evaluate our neural network models since the 90s. Although we must agree that MNIST has aged well and still is much respected in the machine learning community, but it's too damn easy nowadays to prepare a model that can achieve more than 99% accuracy on it. Fashion MNIST is more complicated than MNIST and has been prepared to replace the age-old dataset. So our model is a simple 2-layer convolutional neural net. The input layer is our 28 by 28 grayscale input image. With our first convolutional layer, we apply 32 different filters to get 32 different feature responses. Then we feed those feature responses to our first max pooling layer. The max pooling layer shrinks down the size of our feature responses to half its original size. Then we just repeat the same set of convolution and max pooling layers, this time with 64 different filters for the conv layer. As the final output, after the second pooling layer, we obtain 64 different feature responses, each of size 7 × 7. We then flatten out our feature matrices and pass those through a dense layer for classification. Our dense layer has 1024 trainable parameters, which are activated by the rectified linear unit. Finally, a dropout layer serves the purpose of regularization. We shall talk more about our model shortly. For now, let's open our code. So for the purpose of running this code, we need to first get inside our project directory. Then we can activate our virtual environment. So we can simply type in source activate followed by the name of our virtual environment. So now that we are inside our virtual environment, we can go ahead and install some of the optional dependencies that are required for running this code. We can install these dependencies using the Conda package manager. So the dependencies that we need are Jupyter, scikit-learn, and matplotlib. Now Conda will do the hassles first and fetch the metadata and install the dependencies. Now our project directory already includes an IPython notebook, which we can open up using Jupyter. We need to simply type in Jupyter Notebook and press enter. Jupyter will automatically open up a browser window. Now we are able to see our source file, which is this IPython notebook. We can now go ahead and open this. So in the first few lines, we need to import our dependencies. We shall import TensorFlow, and from TensorFlow example tutorials, we shall import input data, which will help us read our dataset. In the following lines, we can set some global variables, such as the URL from which we are going to download our dataset, and the data directory inside which we shall expand our dataset. Following, we have two different functions for downloading and extracting our dataset. So once the dataset is downloaded and extracted, then we can load our data using the read datasets method. We just need to pass our data directory as argument and set a few optional flags. The read datasets method automatically splits our dataset into training and test sets. Now we can shuffle our dataset using scikit-learn's built-in shuffle function. Shuffling is optional, but it is highly recommended. We may now see the shapes of our training and test set. We have 60,000 images for training and another 10,000 images for testing. As we can see, the NumPy array for the training set has 60,000 rows and 784 columns, indicating 60,000 samples and 784 pixels per sample image. Now we can visualize some of our training data using Matplotlib. Coming back to our model. Our model is defined in this function that takes three inputs: the features indicating the input images, the labels indicating the associated labels, and the mode indicating whether we're trying to train or evaluate our model. So our input is this 28 x 28 image. The first conv layer takes an input tensor of size 28 x 28 x 1, and after applying 32 different filters, the size of the output tensor becomes 28 x 28 x 32. The pooling layer shrinks down our feature responses to 14 x 14, thus giving us a tensor of shape 14 x 14 x 32. Then we repeat the convolutions with 64 filters, followed by another max pooling layer. So the size of the final output tensor is 7 x 7 x 64. Then we flatten out the output of the final pooling layer and pass it through the dense layer for classification. We have a 0.4 dropout rate, which means that 40% of the activations will be discarded or set to 0 in order to prevent the model from overfitting. We can then use the TensorFlow estimator, which makes the training and evaluation much simpler. Finally, we can train and evaluate our model. Now, training will generally take some time, and once done, you will be able to check the final evaluation accuracy. For our case, it turned out to be 90.15%. Now we can use TensorBoard to see how our model performed over time. For this, we need to get back to our terminal. From here, we can run TensorBoard with the logdir option. We need to pass the name of the folder where we have stored our TensorFlow log. Now we need to open a browser window. The TensorBoard service is available at port 6006 on our local host. Here we are interested at the accuracy and the loss graphs. We can see how our accuracy has increased over time and how our loss has decreased. TensorBoard can be very useful to see how our model performs given certain hyperparameters, and we can tweak our hyperparameters based on these observations. So we have achieved more than 90% accuracy on our fashion MNIST task using only a 2-layer convnet. But this is not the end. You can opt for higher accuracies using more convolutions or by stacking up more dense layers. You can also try to tune the hyperparameters such as the number of filters used or the kernel size or the pooling area. Experimenting with these hyperparameters will definitely give you more insight on how to solve this type of problems.